All right. All right. Thanks for the introduction, Constance. So welcome everyone to my talk. It's titled Efficient and Data-Driven Construction of the Bank. So let me go a little bit into words. So before I do so, let me introduce myself. So I'm a PhD student. I recently graduated 2 months ago, and as Constance said, I did my master's and bachelor's at Zurich. And then I did my PhD, just graduated, and mostly I'm working on event-based vision and on the intersection between deep learning, event-based vision, and also robotics. In my free time, I like to hike and bike and ski. So you can see on the right, that's a picture from one of the Swiss hills. So now let's delve into the topic. So one of the main motivations for us computer vision researchers are these biological systems. So why are these biological systems so inspirational? One of the reasons is because they're highly agile. They can perceive their environment and in particular this highly robustly, and they can do this all in a very dynamic scenario with very little compute and very little power. So as computer vision researchers, we try to emulate these systems. We try to accomplish as complex feats by using as little power as possible. However, most of computer vision research nowadays has been devoted to frame-based cameras. So frame-based cameras, they suffer from a number of disadvantages. One of them is motion blur. So in these very dynamic scenarios, like the dog catching the frisbee, we will frequently observe motion blur. This degrades the image quality and thereby also limits the camera potential as we can see these images. You see here the high dynamic range. So as soon as we're looking towards the sun, most algorithms have the kind of saturation, this over and under saturation in the image. And finally, because we're observing the environment with a frame-based sensor, we're introducing an artificial latency, which can limit the safety of the system, especially for example in a scenario like the one on the right. In my PhD, I was trying to address these problems with a new sensor and also a new sensing paradigm, which is incorporated in the event camera. So let me go on to explain a little bit how the event camera works. I think most of you already know, but essentially we always use this little rotating disk as a point example of how an event camera works. Instead of measuring individual images over time in a regular fashion, event cameras only see the changes in the image. And if we now play this video and you see the data that is generated by the event camera, you can see that the changes form this kind of spatiotemporal spiral in the space and environment. And this kind of data representation is highly sparse, it's also synchronous, and therefore it has actually a lot of amazing properties. One of these properties is it has a high dynamic range, and often that it has kind of an adaptive dynamic range. So here on the right, you can see that we can simultaneously see what is outside and inside of the tunnel, because each pixel actually has a separate reference value. Instead, with the frame-based camera, we have to basically have an auto-exposure algorithm that adjusts the exposure based on the ambient illumination. And this means that we, for example, cannot see what is coming from outside of the tunnel. Here I show you how this event looks like in very slow motion. You can see that event here it has a very low motion line, and also it has a very high temporal resolution. So you can actually generate kind of slow motion renderings with events in this way. By contrast, the standard camera has a motion line, especially for example at time of impact with the ball, which is maybe a very important event in robotics application. We have a very high motion blur artifact. Finally, here we see that event cameras also feature a low perceptual latency. This makes them especially interesting for these kind of high-speed maneuvers that we would like to do with robotics. So looking at these examples here, people are sometimes still not convinced that you need an event camera. Why don't you just use a high-speed camera in this case? So let me explain to you what I call this the bandwidth latency trade-off. So here in bandwidth, I mean the data that is transmitted per second, and here the latency I mean how much time you need to wait for the next information arrives. And what you can see is that high-speed cameras, they have a very low latency. You can, for example, even see the 200 hertz. But this means that we're drastically oversampling parts of the scene and are actually inducing artificially high bandwidth on our system. But to reduce this bandwidth, we can actually reduce the frame rate of the camera. But what this does is, of course, increase the latency, so we're not as reactive anymore. Now, because event cameras have adaptive sensing on pixels, they can simultaneously reduce the bandwidth, so they have a highly sparse output, and they can also reduce the latency. Not only that, they also have this thing called, they basically perform well in this thing called the signal latency constraint. So what does this mean? So as you're increasing the frame rate of your camera, you have less and less light that you can integrate between frames. And what this means is that the signal to noise ratio goes down as we increase the frame rate. And this is actually why when you do high-speed photography, you usually need floodlight to illuminate your scene so that you can actually get a high-speed video which has reducing signal to noise ratio. Now, again, because event cameras are adaptive and they don't have this exposure time limitation, they can actually capture data with a high signal to noise ratio, but simultaneously with a low latency. So, having now explained the advantages of event cameras, gives us a lot of hope, but also asks a question. So how can we actually process these events? If events are not images, they're actually these sparse point clouds of data. And this means that we have to design new algorithms. So let me show you one of the early works which were using event cameras here in this example for dynamic object avoidance. So here you can see our drone perceiving the events with the camera mounted on the drone itself, and being able to avoid an object with a 3.5 millisecond perception to action latency. And this is mostly possible because the event camera has such a low perception latency. And you can imagine that, for example, achieving this kind of latency with a frame-based sensor would require a very high frame rate camera, which isn't feasible in this case. This actually allows us then to avoid obstacles at up to 10 meters per second speed. So let's go a little bit into detail on how this algorithm works. Here we see the events observed by the camera on the drone. But remember that these events are actually not images, they're actually these 3D point clouds. And one algorithm that has been very good at basically, so this algorithm basically works by segmenting out the moving object. Then we want to avoid this object. So how do we actually segment out this object? It's by using the measured motion of the drone, which we can do with ironing, and warping the events according to this perceived angular rate. And what this actually does is that it kind of generates these sharp event frames. And you can see that most of the events which are triggered by the background, they are actually quite sharp, which means that they are explained well by the motion of the drone. But there's actually objects in the scene that are not explained well because they're independently moving. And what this actually allows us to do is to do some sort of anomaly detection in the event stream by using this thing called the mean timestamp image. And if we threshold this image, we can actually pretty cheaply segment out pixels which are independently moving in the scene, but also filter out events that may be extraneous enough are not actually needed for the evasive maneuver. And this algorithm has been successfully implemented on this drone here. On the bottom right, you can see the segmentation mask and these white dots. And this is essentially what is needed by the drone to then perform the evasive maneuver. Yeah. So for the motion compensation using the angular velocity from the RV, yeah. How do you handle the translational velocity? So yeah. So in motion compensating the events, there's always these two components. Like there's the translation component, which uses optical form and the rotation component. To successfully incorporate the translation component, you need to do mapping as well. And this is quite difficult to do accurately. And for this reason, people opt to use basically an approximation and saying that most of the motion comes from rotation anyway. And this is usually a good enough approximation to make make basically a halfway successful segmentation. But it's good. This is kind of an approximation, but it works pretty well for this application here. So we've seen now robots avoid objects, but the question is, can we actually also catch objects with this algorithm? And this is what we've tried out with the collaboration with the RSL, where they designed this quadruped robots. And we used one of these quadruped robots, mounted a net on the back, and tried to catch the object using a similar kind of algorithm. So let me go a little bit into detail on how this algorithm here works. This algorithm has two components. One of them is the oil component. It's the controller. Basically, the planning, it tries to align the net with a point called the impact point, which is essentially a point which we assign, which we think that the ball will intersect with this plane centered at the base of the robot. And this we can do actually quite fast because the geometric problem, we can parallelize it. We don't have to render images. And we can train this and that's the parallel with geo and vector. And because we have this abstraction layer, we also have actually decent simple transfer because this impact point is actually quite low dimensional and doesn't, for that reason, no one would suffer from the sim to real transfer that much. So how do we now recover this impact point given a vision front end? Here now I show you again the algorithm that I discussed before. On the top we have the moving object that is the algorithm running at 100 hertz. And with this algorithm, we can now, given a prior on the given a prior on the size of the object, we can now project the object out in 3D and then take a parabola to use to directly define the impact point in the base of the robot. So, so here we see actually quite a few nice applications of high-speed robotics of event cameras. And where do we go from there? So recent years have seen quite an increase in deep learning methods developed for event cameras, especially because of the progress in deep learning. Some of these include object segmentation, high-speed and high-dynamic range imaging, also slow-motion photography, and finally optical flow, also developed in this group. So here we see now kind of a further iteration of this object segmentation algorithm, which now is done with the deep neural network. Here we see that the algorithm is much more robust to, for example, to maybe formal, like not circular objects, but like larger objects like that point plane, and also it's to a certain extent more accurate, so it can actually pursue or evade objects better. However, one of the main challenges that remain is that, so we know now deep learning can improve these algorithms, but only to a certain extent. So we're actually trading off certain things by using deep neural networks. Here I show you these deep neural networks that I discussed previously. They have a very high robustness, but unfortunately, because they treat events like a high-speed camera, they process events densely, they actually also are quite limited because they again use the deep neural network, they use a network accelerator, and for this reason are not actually exploring the potential of event cameras, which is really sparse in asynchronous processing. For this reason, there's a parallel branch of research which tries to co-design the algorithm with the event data, and thereby tries to achieve a higher efficiency in the algorithm. But because they're mostly using either shallow machine learning methods or have not as mature learning techniques, they're usually limited in terms of the robustness. So they rarely scale to very complex problems. So going back to our goal, we see that biological vision systems are kind of somewhere in the top right. And this has been the goal of my PhD. How can we actually reconcile the advantages of both of these paradigms to get both robust and efficient processing? So let's go into what is actually the core problem using deep neural networks with events. So here I show you a sparse point cloud of events. Remember, there are these kind of sets of points, and we want to process them with a deep neural network. But usually deep neural networks, they take images as input, or at least CNN input. And to therefore bridge this gap, we have to incorporate a few pre-processing layers. And these pre-processing layers, first of all, grab windows of events, so fixed windows, then aggregate the windows into fixed frames, and then process these frames as if they were images. And then they give an output, like, for example, the output on the right. If we, a lot of papers also combine them with images, so then images are usually used to synchronize the events. So you tell you exactly when does this time window start, and then you can take as many events as you like. And then these events are then concatenated with images to process the event, to process the object detections. So here we have a few advantages. We have negligible motion blur. We also have a high dynamic range. We're actually using the high dynamic range of the low motion blur of the events in our deep learning system. But unfortunately, we're actually lacking in terms of the high temporal resolution and the low bandwidth properties of events. And this is chiefly because we are introducing these two pre-processing steps. Time windowing and framing basically remove the high temporal resolution and the sparsity in the event stream. So now let us look at how event representations are constructed. So here we focus on this core building block, the window of events generate frame input. And now the question is how is this usually done? So there's a rich kind of literature on this, which I will use histograms, box figures. They also use sometimes unifying samples, and also mixed densities, so we get different window contexts. However, all of them have one thing in common, which is to find them or to validate them, you usually have to stick a neural network at the end, train your neural network on that representation, and then check the validation score. And this is usually how they are then sold in the window. So they say our representation achieves X% improvement in the validation score. And so this is kind of a nice cycle, but it's quite slow because you have to train a neural network each time. Each time you want to kind of change your input representation, it also means that your memory state basically is dependent on your network. You set the test actually becomes important to certain extent. So one question, since we anyway want to move away from anyway we want to remove this red block, is it does actually can we actually somehow measure this faster, and in particular can we, for example, look at how much data information is being lost when we go from raw events to these things, and maybe use this as a measuring stick to find out what are the representations that we should use. So this has been a recent paper where we use the normal process time discrepancy, which is a metric on probability distributions. It basically compares the raw events at onset and tries to transport them into the event distribution. And what it tries to do is it tries to retain the similarity between events which are mapped to the output features. So if two events that are input into this pipeline here are far apart, we ideally want them to be mapped to features which are also far apart, so to kind of retain the distinctiveness of the event. And in this way, we can somehow measure how much information is lost. So ideally, if you have, for example, 2 times for raw events, then this information would be 0, and loss would be 0, because we could just map every event to itself. And now we can look at how does this grammar passage time compare to the validation loss-based comparison. First of all, it's much faster to compute. The 200 times faster, and also there's no network there. So it means we can actually make this claim about event representation much more general and not tied to a specific network architecture. So how does this discrepancy compare against the past component? So here we show results where we compare the found loss in information, which is the lower is better, and the past performance of the network trained with that specific representation. We also show different network backbones, and not shown here, but we also tried this for different tasks, and they all came with the same conclusion that as we are reducing the information that is lost, we also increase the performance of the network that is trained on that representation. Not only that, we also found that if we now use this metric, this discrepancy here, we explicitly optimize it. So we can do this with Bayesian optimization. We can actually find representations which are further down and therefore also further right. And here we start. But essentially, we found a neural network representation which is now 1.8 MAP higher, just by searching a very large set of representations. Yeah. All right. So every one of these points is a single neural network, and it was trained on this detection benchmark, then prophecy then one, and it has so for each horizontal line we have a different event representation put over, but the network are the same, and as the different colors show different backbones. So we have a swing backbone, the efficient backbone, and the resonant backbone on the network. And then after training the network, we get a specific object detection score. And at the same time, we can measure how much information is, for example, lost when we use the time service. So we then compute the information loss in terms of probability between that and the time service that we generate from the events. And you can see, for example, that if we have a time service, then we are actually reducing the information content by little. And if we, for example, use a 2D histogram, which aggregates all the depth of time onto a single pixel, then we actually have more information. And this actually shows, and the main highlight here is that there is a correlation. If we reduce the information loss, then we also increase the performance of the network trained on that specific.
How do you fix
Exactly. So it's basically these. So imagine you have on the left side like this, and then on the right side you have different. So if we have, for example, this compared to that, then we have a high loss because we are compressing all the time into one of the channels.
Dependent on how long the window is.
Yeah.
Or the website
Exactly.
each blue point has like a more than outcome.
Exactly. So every one of these has additional hyperparameters, which are like here. And for example, exactly time is one. Number of discrete identification steps in time is one. There's also like, for example, if you look at this phase surface with like 90 constant. What we want to basically show is that changing basically this, changing these changes the information that is lost. And going from events to
I don't think the voxel grid has less information, has more information lost than time purpose. Or is that in the context of
so I think
tasks?
yeah, no, this is actually this is a bit so this time surface here is actually multi-channel. So we control for a few hyperparameters, like for example the number of channels that we use. So in each one of these experiments we use 12 channels. So we use 12 channels for the voxel grid. Because we saw, for example, if you increase the number of channels, of course, you reduce the information loss, but you have less loss to the information. And so we have here 12 channels, here 12, and then also for the time surface, we try to do 12 we sample the time surface at 12 separate instances.
So it's more like box over time surface.
Exactly.
Rather than
Exactly.
okay.
So, okay, so this indicates that there's actually a correlation between information and task performance. So ideally, we want to just eliminate pre-processing, right? Because any pre-processing will reduce the information. And what this actually means is can we go directly from raw events to deep learning output? So in studying this literature, we see that there's 4 different kinds. I mean, there are probably other ones as well, but I identified 4 different kinds of processing events, each come with a separate kind of network architecture and challenge. So on the left, we see spiky neural networks. Spiky neural networks are a bit hard to train because they have approximate backpropagation rules that we solely gradient to define a gradient for them, and this actually limits sometimes the robustness of the methods. However, they have a few positive aspects, which are, first of all, they code like locality into events, spatiotemporal, and they can also process events event by event. So maybe these two will become more clear as I go through other methods. Some papers also process events as point clouds. So remember there are point clouds. Point cloud methods are kind of mature at this point. They have efficient backpropagation based on efficient training rules based on backpropagation. However, because the point clouds are usually considered as unordered sets, we don't actually have the notion of which point clouds are close to each other. Additionally, point cloud methods always process them in batch, so you cannot efficiently insert the new point. You could do like a new event arriving and then update the information. So they're not asynchronous. Graph neural networks kind of innovate, and they kind of improve this following aspect because now they can connect the nodes, and the nodes can now display the information. This means that we can actually learn local structures in the event stream, but still they are processed in batch. And finally, there's also submanifold sparse combinations, which treat events like submanifold embedded in 3D space, and then do a convolution along with submanifold. So they can enhance the efficiency, but again, they're not asynchronous because they have to process events in batch. So I was mostly interested in these last two contenders. They have all of the, they kind of check all of the boxes, but one of the main limitations is that they're not asynchronous. What this means is that we have, so then my question is, can we actually convert these models into asynchronous models? And this is indeed possible with something called asynchronous neural networks. So how do asynchronous neural networks work? They train a network with batches of events. So in a standard way, like many people do, they use batches of events, they put it to the network, they supervise, and they train the weights of this network. But then we also leverage sparse neural network styles, like for example, the graph neural network or the submanifold neural network. What this allows us to do is actually retain the efficiency of computation by using sparse activations. And then we deploy this network. We actually essentially copy over the weights, and then we try to formulate update rules. We try to reformulate the computation rules so that when we now feed events as a stream, we get exactly the same output as when we were training it. So how would one of these kind of updating schemes look like if we did completely naive computation? So imagine now you have a window of events, you process them, now you get a new event. The most naive way to incorporate this new event is just to reprocess everything with the new event added. But actually, events only give very, very localized information. And this means that we actually don't have to recompute most of the parts of the network which are not close to that event. This means that we can actually formulate these things called the sparse update rules, which only update subsets of the network as the events arrive. And this, using these two principles, sparse activation and asynchronous updates, we can efficiently enhance we can essentially enhance the efficiency of these neural networks without losing anything in terms of performance. So here, let me show you again a little bit more detail how such a sparse update would look like for a graph neural network. So we have here a graph of events. We're processing them in sequence. And now imagine we get a new event at timestamp t. So that graph neural networks, they send messages between nodes. So essentially, if you wanted to get the exact same output as if we were processing a new graph, we would actually have to update the one hop neighborhood of this graph one layer down. After n layers, we have to update the n hop neighborhood of this graph here. And essentially, we don't touch any of these nodes here. We only complete these guys. And after a pooling operation, we have basically this. And this means that you can see that we're actually only reprocessing a subset of the nodes. Now, the question is, how small is this subset? So to quantify this, I plot all the methods on two axes. One of them is the performance axis, and the other one is the flux per new event. So how much computation do you need to incorporate new event into the prediction? So here on the right, you see CNN-based methods. They're quite high in performance, but they also have a very high computational burden. So I implemented these asynchronous networks in two instances. One of them is Asynchronous. This is a submanifold convolutional network, which basically updates only the subset of the nodes, and you can see the subset in green. You see that it's quite a bit more efficient. It's about over 100 times more efficient, but also because we were using quite shallow networks, they're also quite low in terms of performance. So how can we do better? So one way to do better is to use graph neural networks. Graph neural networks also take into account the temporal aspect of events, and they have more flexibility in the connections that they can make. And here you can see now like a subgraph that has been updated at each event. And now plotting this event graphs, we see that we can go at the same time much more efficient. And because we're going much more efficient, we can actually also make the networks deeper. And what this allows us to do is now actually reach a point where we're on par with the feed-forward neural network here on the right, but around 5,000 times more efficient than doing just a standard using the CNN, using a feed-forward CNN. Yeah. Exactly. You remember them. There's no detail on activations because the goal in formulating this synchronous processing is to have the identity. And so you really just try to take the forward pass and write it in reverse way. Remembering all the activations that were before. If you lose in that, then this also produces an update basically. So there's actually two revisions. There's one inserting, and there's one taking out. Yeah, this one. Yeah. So, okay, so we see we have one last gap to propose, which is how do we reach the performance of a recurrent neural network? So to study this problem, let's look at how a feed-forward network and a recurrent network work by looking at this static scene. We can see that the recurrent network is able to detect objects even though they are not generating events. And why is this the case? Is because it can actually leverage a recurrent embedding, which it always carries with it, and then try to predict objects which are maybe not visible at the moment. And what this actually points us to is that we need something called motion invariant representation. So when there's no motion, we still want to have a representation that we can go back to and take make a prediction. So I tried to incorporate this kind of insight by combining events with images. Because images are essentially like motion invariant representations. And let me show you now a few instances where I try to combine these modalities and to basically achieve this. So here we have an example of asynchronous feature tracking. It uses images to initialize corners and then uses the events to track these corners. So again, we have an invariant embedded and invariant representation here, and then we are basically tracking the representation using the events that follow. Using this paradigm, we can see that we can track features with a very high speed, and also in a very high temporal resolution, where, for example, the frame-based method, we started using magenta points with this track because you have quite large displacement and also significant motion growth. Another instance of this combination is event-based, then the frame-based video framing population. Here the goal is to use a low frame rate video with infinite events and then generate a high-speed video like that. So bring like the first of the data control. And this is also an instance where we had to design an algorithm to propagate information in the from frames into an intermediate timestamp using events. And the way that we achieve this is by using a specially designed neural network, which uses parametric flow. So one of the branches of this network uses events to estimate motion. And this, it does this in a parametric way. So you can insert the timestamp, you can process this time, and then you can insert a timestamp whenever you want and reuse the features from this network to get the features from the image transported at different timestamps. And then there's a second branch which uses the image and events and uses them together as if they were just added together. So directly incorporating the change measurements into the image to get the feature. And then both of these features are fused and decoded into the output of the network. We can see that actually, since video framing population is a non-causal process, it's simply to record the video and then you generate a high-speed video with post-processing. You can actually use the past and the future frames symmetrically to get more information for the recording. So again, you can see this this nice pattern where we're using images as invariant representations, mapping them to the intermediate frame, and also using events to do this. Finally, here are some of the results of frame interpolation. One of them is due to enhanced nonlinear motion estimation. Here you can see during rotation, the corners of the umbrella actually prescribe the circular motion. And it is actually quite challenging to model with a frame-based sensor. Yeah, this video doesn't work, sorry. So what you should see here is that as we are rotating the umbrella, because it only has two access to two images, it thinks that the trajectory between the two images is linear. And what you will see is that the corners start to truncate as we are moving from one frame to the next. And this is the case because the frame-based method is limited in terms of what kind of motion you can reconstruct. You can only reconstruct the linear motion, whereas an event camera can actually reconstruct the full rotational motion. Here we have, okay, same problem. What you'll see here is that we have here a fountain where the waves are moving down, and with the event camera, we can actually get a very smooth slow motion footage of this. And with the frame-based camera, because the frame rate doesn't actually allow us to find out in which direction this wave is going, because the frame rate was so low that it thought that actually the wave is going up. And this actually is an instance of visual aliasing, which is the second limitation of frame-based methods. So they cannot sometimes match the correct features together. So, okay, so we've seen now two instances. We also saw a deep learning method. However, this deep learning method still doesn't incorporate sparsity and asynchronous into the processing paradigm. So how can we actually do this with events? So this is what I've tried to achieve with hybrid asynchronous object detection. Here you see a neural network that combines a asynchronous graph neural network that processes events with the standard CNN that processes the images. In its operation, it uses the image to generate object detections. So even for static objects, like for example on the right, and then it uses the events generated. Okay. Some of these, I think these videos are not working. So the asynchronous graph neural network will then use events to propagate the detection forward in time. So as we're gathering more events, we will see this object detection move in the way that the screen is moving in. What this actually allows us to do is now we don't have this limitation more that you have to wait for the next frame to see what is happening. You can actually use the events to already get a pretty good idea before the next frame arrives. And here I show you an example where on the left, the event camera already has the event and frames. They already have sufficient information to detect this pedestrian trying to run onto the street. Whereas if we only focused on the images alone, we would have to wait another few frames to see this pedestrian move. Here is another example of a kind of challenging HDR scenario. We have this car approaching, and because of the saturation, the frames are not enough to actually find the car. But then adding events again enhance the contrast, and then have an early prediction of where the car will arrive. Here's another example where we have this kind of low dynamic range. Again, with the events, we're able to detect it faster. And finally, here are two examples in low dynamic range, where maybe you can see it with the light. So there should be a pedestrian. You see here the sneakers of the pedestrian, which we can actually detect with the event stream because of its high dynamic range, where in the frame camera you cannot see it at all. So let me also explain to you how this looks like quantitatively. So what I'm talking about is events can actually see the blind time between frames. And how do we quantify this? So we can actually look at an object detection score over time between the consecutive frames. In this case, 50 milliseconds corresponding to 48 years camera. As we are getting more events, the object detection score remains roughly similar. But if we, for example, only use images, the object detection score would decrease. And this decrease is actually because the labels of the object detection, they misalign as we're going forward in time. So we're actually comparing the ground truth with a more and more outdated object detection here at timestamp 0. This actually also shows that if we reduce the time window, we can actually reduce this worst case decrease in performance. So meaning that if we have a higher FPS, we can actually also get a better performance. This is what's shown here. As we are increasing the bandwidth, essentially the frame rate of the camera, we are increasing the worst case performance of the object detected. And one of the nice things about now looking at it in terms of bandwidth is that we can actually place our system also into this chart. And we can see that at a bandwidth that is roughly the same as a 45 FPS camera, we can achieve a performance which is on par with a 5,000 FPS camera. And this basically shows that we can replace the high-speed camera with our hybrid setup with a 20 FPS camera and an event camera. And by doing this, we can actually increase our worst case object detection score by 2.6 MAP. So going back to the outset of this talk, I hopefully convince you that that we were able to combine useful elements from both classes of methods to get both efficient and also robust deep neural network. However, we're still a ways off from biological vision systems. So let me just summarize the conclusions and then wrap up the talk. First, we saw that event-based algorithms are very useful for robotics tasks like high-speed hyperalgorithm or object catching. Then we saw that, well, a lot of people are now using deep neural networks. And actually, one of the key indicators for how good your event representation works is to study how the information loss goes from events to event representation. Then we saw that removing event representation is actually quite useful. And when we do this, we can actually use the synchronous and highly efficient local recursive update tools. But in order to overcome the gap to the current methods, we need to use some form of local invariant representation. In our case, we use images. Finally, we saw that when we look at this combined system, images and events, we find out that images are very good at predicting stuff, and then events are used to propagate this information. And what this allows us to do is to replace a high-speed camera with a low frame rate camera plus an event. So with that, I'd like to thank you for your attention. For those who weren't at the workshop, event-based vision workshop, there's a link there where you can find more resources. Also, a list of papers is available here if you're interested. And now I'm open for questions. So it's actually really detected. It's not acting. It's kind of this thing. So the object detector doesn't assign any ID, and you're just updating the detection scores as you're inserting more events. So you're kind of redetecting the same object multiple times, but this looks like it's basically tracking the same object. It doesn't require that you do the effort. So you could run this completely without the image-based method, but then we would have a kind of reduction in the performance because of this static. No, I'm just saying that the event detection branch in fact is a full-fledged object detector. It can also detect object platform, but it's combined in this way to use it.
So staying topic on the hybrid system. So you've shown that you can initialize vectors or you can set objectives just like in the case where you don't put one after car.
Yeah.
So I'm just curious what the advantages are of there also using RGB frame, especially in conditions where, say, in the case of the pedestrian in the document.
Yeah.
You see from other sensor fusion approaches that when you're using information from multiple sensors, if one sensor is severely degraded, it can hinder the performance of the other by using them together. So can you also have a non-inflection point? The benefit is
so I haven't studied exactly whether the bad image actually deteriorates the performance of the event camera. But in our case, unfortunately, in the video that didn't play, you could see that it could actually still detect the person. But it's a good question whether this was despite the image sensor degrading its performance or somehow helping the image sensor. I don't know what one of the answers to that. Yeah. I had a question about time scale. So what is the expectation of the integration time of the time? Yeah. So the integration time is right. Yeah, the integration time is actually the time window that is studying. So it's a time window of events And then this is kind of hard-coded parameter. So it integrates all of the information in a time window, but it doesn't have more memory than for example, that. I think it would be maybe useful extension to also have even a longer time window. Yeah, that would also be. So one way would be to adopt maybe one of these multi-density stack approaches where they look at exponentially growing time windows of events, like one maybe 1,000, 2,000, 4,000, 8,000, 16,000, like in this order. And then you can have maybe multiple branches which are in parallel processing. That could be one of them. Yeah, so that's actually true. So searching for is actually an overhead to your computation. So and in particular because we're doing random access, it also slows down. But this is mostly hardware dependent. So it's because it's implemented on the CPU accelerator instead of maybe ASIC or PPA. Yeah, but that's true.
But I found it was going to do.
Yes.
And for you, I guess, attach to parts and go from the tab.
Exactly. So there's some approaches to accelerate this. So for example, there's a nice implementation of a graph update, like an updatable graph structure which uses event queues. And what it essentially does is from the insert and remove end, instead of having to compare with every node, you only compare with a small radius around that event. And that actually allows you to be much better in speed. And if you could implement this on every layer, you could probably circumvent the system. Because we have, so one detail that I didn't mention is that the graph is a radius graph. It connects nodes which are a distance lower than a specific radius apart. And this means that when you're searching for nodes that are connected to this node, you don't have to search all of them. You can only search for local upper bound of this. Yep. Thank you everybody for joining, and thank you Daniel again. Very helpful.